Okay, good afternoon. Our speaker today is Gianluca Castignani, who did his undergrad studies at Normale in Pisa. Then he got a PhD in CISA in 2014. Then he went to France for several postdocs. He was fellow at the observatory in Nice. Then he moved to Paris, and then in Switzerland, in Lausanne. And since 2021, he's a postdoc at the University of Bologna. He's an expert in extragalactic physics. He's part of Euclid. And today he will tell us about distant brightest cluster galaxies. Please.
Yeah, thanks, Franco, for the nice introduction. So yeah, today I'm going to talk to you some projects I've been working on since last years. So in fact, I remember that I was here in 2019 for the last one of my last talk. So I will talk to you about what I did in the meanwhile. A little bit loud. Okay, yeah, sorry. Okay, sorry, my voice is a bit tough. So I will talk to you about the galaxy clusters and why them, because they are in fact the most massive gravitationally bound structure in the universe with large massive sizes and a lot of galaxies. You can see here nearby Hubble cluster, where you can see a nice aggregation of red and dead galaxies in the center, and also strong lensing features. And indeed, galaxy cluster are extreme objects that are originated by gravity or primordial perturbation of the density fields, and now they appear as massive structures. And they are also key laboratories to study galaxy evolution in extreme conditions. And indeed, some prototypical examples are radio mode AGN feedback. As you can see here on the left, the Perseus cluster, where at the center is the Perseus A BCG, that is radio galaxies and is able to launch powerful radio jets that release energy up to the cluster periphery. And we can appreciate it as, in fact, for example, some characteristic ripples in the X-rays, indicating possibly sound waves propagating outwards and preventing the strong ICM cooling in the center. On the right, instead, we have another example of extreme galaxy environment interaction. It's a famous RAM pressure strip galaxy in the NOEMA cluster. And as the galaxy enter in the cluster, the interaction with the ICM is able to strip gas that you can see here with a long tail, and we can see in multi-phase, not only ionized gas, but that's molecular and also even hot X-ray gas. So altogether, that environment are known to be a strong processor of galaxy properties. This is known since the early studies by Brightest and many others after that. It is also known that the BCGs, that are the brightest cluster galaxies at the center, are associated with radio galaxies, and they are responsible for this radio mode AGN feedback mechanism. Together, this is what happens locally or in general for clusters, but it's also key to study how BCGs in particular and clusters evolve with time. And indeed, the BCGs are known to form at very high redshift, with several episodes of tri-mergers. But there are also several studies that show that possibly they also have several episodes of star formation even later. At some point, also at higher redshift, we should expect a reversal of the star formation density relation, and this is also quite debated for clusters and distant protoclusters. And concerning particular molecular gas, we know that higher protoclusters are have in fact large molecular gas reservoirs, but this is not clear what's the fate of this molecular gas as we move to non-virialized protocluster down to virialized clusters at high redshift. And with this in mind, I mean, I performed and I led a systematic search to study the molecular gas in distant cluster galaxies and BCG in particular, as indeed the molecular gas is a raw material from which stars form. So it's really key to understand the ongoing star formation. And this is part of what I'm going to tell you is part of a large campaign to observe CO in distant cluster galaxies and BCG in particular, mainly exploiting IRAM facilities in single dishes with 30 meter and then NOEMA interferometry in the French Alps. So this is the first study that I'm going to show you. It's the study of distant BCG at 1.7. Is one of the most distant ones. It's very peculiar, as you can see Indeed, within a few tens of kiloparsec in size, there is a very complex morphology and messy structure. It's very different from the other cluster that I showed you before. Indeed, this cluster has a star-busting core, several hundreds of star formation ongoing. It is very extreme. And indeed, when they observe with the LMT in single tissue observation CO, they found a large molecular gas reservoir that they suggested to be associated with the BCGs, but the beam is an unresolved old structure that we see here. And with this in mind, we wanted to prove it and resolve at high resolution the molecular gas. And that's what we did with NOEMA in CO43. And with KiDS surprise, we found that the BCG is instead gas poor, while the gas is contained in the nearby companions. You can see the merging members in the north, and also a southern companion with a long tail that is possibly the most dense jellyfish galaxies, as this tail is at the beginning of the tidal tail. It was also found in previous studies in stellar emission, and is also we detected also in continuum. On the right, in the dust continuum in the religions regime, while on the right we see that there are two emission from two companions that are near close with respect to the BCG in velocity and in projection. So we are talking about really the cluster core, and indeed these results suggest that these gas-rich members will potentially merge with the BCG itself, and we may also see the reverse of the star formation density relation ongoing. In general, this is also one of the first time that we can prove the assembly of distant BCGs in such great detail. I have to say that there is also the alternative scenario that there is a compelling that they claim that instead there is strong ICM cooling due to runaway cooling the ICM, but I mean we disagree with this scenario, as in fact we basically see that the CO is not associated with the ICM, but it's associated with the companions of the BCGs and clearly gas poor. Okay, so the second case that I wanted to talk to you about another distant BCG is very peculiar. It's 3C186, where actually one is a famous BCG, a quasar of a cool core cluster. And why is it famous? Because in fact, Chiaberti et al. And subsequent studies found that there is a peculiar offset with respect to the isophoton center of the BCG and the position of the quasar of about 12 kiloparsec in projection. But not only that, there is also a stunning shift that is very puzzling between the broad region emission that we believe are associated with the black hole and the quasar, and the velocity of the narrow layer region that we believe are associated with the host galaxy itself. So to explain both the projected and velocity offset, a scenario that previous study suggested is that we are seeing a gravitational wave recoil, in the sense that after the merger of the parent galaxy and the formation of the BCG, given in a peculiar configuration of the spin axis of the black holes, there may be an isotropic gravitational wave radiation that results in an ejection on the black hole that we see, and then we see in terms of this projected and in particular velocity offsets. And we wanted to prove, to confirm this scenario with high resolution NOEMA observations. That's what we did at observing 1 millimeter and in CO43 and in continuum. And in fact, we simultaneously confirm both the projected and the velocity offsets. This is one of the first cases that this is done, and in fact, similar observation by De Carli were in fact able to rule out another candidate, a gravitational wave recoil candidate. While in this case, we strongly support the gravitational wave recoil scenario, as in fact the molecular gas reservoir in green you can see here is clearly offset with respect to the position of the black hole, and the molecular gas is co-spatial with the host galaxy, and while the continuum emission is co-spatial with the QSO. So the interpretation is that the black hole is literally kicked off out of the galaxy after the merger, and we also have this confirmed 2000 km/s shift. So this was a strong result that we obtained with NOEMA, and then I wanted to move to another set of projects that we did in collaboration with people here in Bologna. And it was to search for CO and intermediate redshift BCG. So we moved to lower redshift, and this population of star forming and intermediate redshift BCGs are an intermediate transitioning population between local BCGs and star forming ones at higher redshifts that I showed you before, and are also the high redshift counterpart of local star forming BCGs. And we did the systematic search based on several IRAM 30-meter programs, targeting both CLASH BCGs and KiDS BCGs. So we first studied with CLASH, as it is a famous survey, is ideal for lensing study, as it has contained massive cluster and intermediate redshifts. But it is also ideal for galaxy evolution studies, as it has a wealth of ancillary data in photometry, spectroscopy, and multi-wavelength. What we did in particular was to target 18 CLASH BCGs in the northern hemisphere, reaching 82% completeness in the northern hemisphere, targeting several CO lines. We also have star formation rate based estimates, star formation rate estimates based on UV and H alpha by previous study by Fogarty et al. And are useful for our analysis. And in particular, the main result is that out of 18 BCGs, only 4 were tentatively detected in CO. So this already tells us that gas-rich and star-forming BCGs are extremely rare. And however, we found one that was detected, that was RX1532 at 2.4. It is clearly detected in 2 CO line, and this is a very peculiar object. As you can see, this BCG is very messy. It doesn't have a standard elliptical morphology, but it has a lot of filamentary structure ongoing, and also the star formation rate map shows a elongated filamentary structure, while we observed this BCG within the beam that is the white circle, the IRAM 30-meter beam. Overall, it has a high star formation rate of more than 100 solar masses per year. And that's what we obtained. We obtained that, in fact, we detected this BCG in 2 CO transitions, CO1 to 0 and 3 to 2. This is one of the first time that intermediate redshift BCGs were detected in 2 CO lines. And with this high molecular gas reservoir of about 10 to 11 solar masses, the gas is also strongly excited, about 0.8 in excitation, and high gas fraction of 0.4. And then now we also have a new high resolution observation, not only of these BCGs, but also other BCGs with NOEMA, and are ongoing, and we will distinguish, in fact, between different environmental processing at high resolution that are responsible for star formation and mechanisms can be cooling flow, molecular gas intercompanions or mergers, and so on. And so more will come. But based on these results, in fact, we were already able to put our sources in the star formation in the y-axis, and on the right there is a molecular gas, while in the x-axis we plot the central entropy based on X-rays from previous study by Denowe, and on the vertical line shows the separation in the region where there are cool core clusters here at low entropy levels. So quite interestingly, the red points are the points from our campaign with CO detection or tentative detection, and there is RX1532, but also MAX 1932 that was previously detected with ALMA in the southern hemisphere by Fogarty et al. So with this analysis, we were able to find that, in fact, quite interestingly, the detection of large molecular gas reservoirs, in particular for the two that are strongly detected, is possible when to condition, of course. So first, we should have high levels of star formation activity that, in fact, that are fueled by molecular gas, but also the presence of cool core is key, as it favors, in fact, the condensation and the inflow of gas that triggers star formation, and we see it as a large molecular gas reservoir. So this mechanism is driven by, in fact, by the presence of cool core clusters. And this we wanted to investigate even further by extending our search for large field surveys like KiDS. And in fact, from this previous study, we understood that star forming and gas-rich BCGs are extremely rare. So we had to make a systematic search for distant star forming BCGs, and that's what we did in the KiDS survey with a large survey area of 700 square degrees. And we started from the parent sample of Amico clusters and BCGs by previous studies. So this is also very important to use KiDS, as it has a lot of ancillary data in photometry and multi-wavelength and in spectroscopy that is a prior for our search. And indeed, our sample our parent sample consists of 1,500 BCGs with spectroscopic redshifts, and out of them we were able to select only 6 potential good candidates that have high star formation rate of 20-30 solar masses per year and large infrared luminosities compatible with beam layers, more than 10 to 11 solar luminosities, And also the selection was based on the 22 micron of WISE. But you can see here that overall the densities of these targets show that these sources are extremely massive, with more than 10 to 11 solar mass, and have a strong UV axis and a lot of ongoing star formation from far infrared emission with dash. So there are extremely strong cases to be star forming and to be detected in molecular gas. We also performed color magnitude diagram, and we found that indeed these our BCGs have blue colors. And when we model with color magnitude with red sequence modeling, we found that the colors are compatible with recent bursts of star formation, maybe due to impulse or mergers. But yeah, this is we don't know it yet. I mean, altogether, when we observed, in fact, these 6 BCGs with IRAM 40 meter, we found that 4 out of 6 are detecting CO and multiple lines. This was the highest detection rate for BCGs, and again, we found large molecular gas reservoirs for these sources. So the interpretation that the BCGs that we have are caught in the peculiar phase of star forming and gas-rich phase before they ultimately quench. And then they ultimately become as local passive BCGs. So also we were, thanks to this data set, we were able to put our sources in excitation diagrams. And in fact, here you can see that 4 our sources are KiDS BCGs, and that's we have the 2 BCGs that I told you before. So this was one of the first time that we were able to put our sources in this plane, when we here show you the excitation versus the specific star formation rate. And we see a nice correlation between the two, also in terms of star formation efficiency. So this is the first evidence for BCGs, in particular distant ones, and also before it was only known for other local service like X-cold gas and distant very luminous infrared galaxies and gas rich. So the interpretation again is that we support our interpretation that very excited gas is found only in extremely star forming BCGs and cool core, where again gas seems to favor the high star formation and gas excitation. In fact, the ones that are with high excitation are again in particular the two that are in clash with hundreds of solar masses per year in star formation. So for the last for the last part of the talk, I don't know how much time I do have.
7 minutes.
Yeah, I will talk you about in general about the evolution between galaxies and BCGs, supermassive black holes and cluster, with a number of projects that we did this year. So this is a project that we published. I mean, it was accepted for publication just yesterday, and we in fact studied the environments of distant sub-millimeter galaxies. They are known to be massive galaxies that are possible traces of distant proto-BCGs, but it is still debated if SMGs are really good traces of proto-clusters. What is known is that they have a strong clustering property, so they cluster, and their population is extremely abundant at the peak of the cosmos star formation rate density. So we did the first systematic study of the environment of SMGs, and our sample comprise 12 spectroscopically confirmed SMGs in the Goods-North field, and with spectroscopic ratio between 2 and 5 based on CO emission. We also use for our search of proto-cluster 3 different photometric redshift catalogs that are complementary in redshift, star formation properties, and multi-wavelength properties. And here you can see that the 3 different catalogs probe different redshifts ranges. So overall, we applied the Poisson probability method classifier that I developed to search for dense environment around these SMGs. This is, in a nutshell, it's an effective field theory based on the photometric redshift realization. It relies on a positional prior like radio galaxies, and it's tailored to find distant proto-clusters in the regime of low number counts as shown noise. And some interesting cases are Cosmos FR170 and 2.6, that is proto-cluster candidates that we also detected in molecular gas, the P8 BCG, and that's a Cosmos FR1 at 2.5 that was also spectroscopically confirmed by Dinier et al. Later. It also has a wavelength extension that allows us to evaluate the mid-centering and characterize the overdensity in projected space. So basically, the method works in this way, that we have a position in the sky that it can be a radio galaxy or the SMGs, and we first tessellate the projected space with the given circular tessellation, and then we map our number counts in what I call the PPM plots, where we can see that there are different patterns in this space in redshift plane, where on the x-axis we have the redshift, different redshift along the line of sight, while the y-axis is the redshift being considered that is a sample. So there are several patterns that are the color ones indicate the presence of several overdensities along the line of sight around that given field. And when a given pattern is associated with the spectroscopic redshift of the target, we claim to have an association between the overdensity and the SMG over the radio galaxy in this case. And in our case, indeed, we were able to find some distant protocluster. Like this one is a very distant one that was originally found by Dadi et al. When we found again a high signal to noise at redshift 4.1, and the overdensity is centered with the position of the SMG here at 0.0. While we also have a new protocluster that we discovered, like this one is a 2.2, and also this one at a new protocluster 5.4, so very distant ones. And overall, sometimes they are centered, sometimes they are offset. This is 1 megaparsec radius circle. So overall, they have complex structure, and their size is a characteristic of the core of 0.51 megaparsec. We also, overall, the main results are that we found that the vast majority of SMGs are found in overdensities or in protocluster in general, and it is a confirmation that SMGs are excellent tracers of distant protoclusters. And you can see here the results of a strong agreement between the redshift of the overdensity and the redshift of the spectroscopic ratio of the SMG, between an accuracy of 0.04. And these protoclusters are also excellent tracers, excellent target for JWST, I would say. And also we found this nice, I think, correlation between the molecular gas reservoir of the SMG and the signal to noise of the overdensity. And the interpretation is that, in fact, the SMGs that live in strongest overdensity likely experience most of the galaxy-galaxy interaction, and therefore gas inflows, and that trigger a high level of star formation, and that we can see as a high level of gas content. So in the very last minutes that I have, I wanted to talk to you about a very last project that again was published this year by Poisson et al. That is a student is also looking for a postdoc that we have in Paris. And so what we did, in fact, was to study a distant population of radio Loud AGN using selected in different wide field surveys, and in particular SDSS and gamma survey. So we selected in radio 42 radio sources that are radio Loud AGN of radio galaxy, and that have a multi-wavelength photometric information from the radio to the UV. That allows us to estimate jet, supermassive black hole, stellar properties, and accretion properties. And you can see here the SED modeling of these beasts. That you can see that they are typical of elliptical galaxies, and while there are strong dust emission possibly due to star formation. But also we have broad emission lines, and that's what for all these 42 by selection, and that's what was key. In fact, we were able to estimate supermassive black hole mass estimates based on single epoch measurement and several lines, Palmer lines, magnesium 2 and carbon 4. And when we plotted our sources in the black hole star formation plane, we found that these sources have high black hole masses and high stellar masses. So this is known. It's in fact radio Loud AGN are associated with the most massive black holes and stellar masses. But what was surprising is that they are also overmassive with respect to the scalar relation. So there is a population of overmassive, supermassive black holes. And this was quite unknown at this redshift, and quite new. And in fact, you can see also here that when we plot the molecular gas stellar mass, the black hole mass stellar mass ratio as a function of ratio, we found this population overmassive, supermassive black holes. While the comparison sample is radio quality AGN. So this population does appear only for our sample of radio Loud AGN, and in a fraction of 70%. And we wanted to, in fact, investigate, understand more this overmassive population. And in fact, it's known that the cluster core lit up galaxies are outliers in the black hole and bulge relation. This is known for local studies. So in the IRAM universe, I think this was one of the first studies that showed this, and we proposed a radio mode AGN feedback scenario where, in fact, the stellar mass assembly of the radio galaxy of the radio AGN is halted due to the radio mode AGN feedback, while due to the jet interaction with the environment, while the black hole continues to grow via accretion, and we see it as overmassive. So this is an interpretation consistent with local studies, by, for example, Twilio et al., but they focus on local sources. So further investigation is definitely needed for to understand the megaparsec scale environments of these sources, like clusters or in general groups and so on. So here I leave you my conclusions that I presented you a multi-wavelength project to evaluate in general the impact of clusters in processing cold gas beam star formation. I talked you about processing of gas in distant BCGs, where I led one of the first systematic campaign to observe molecular gas in distant BCGs. And we have also ongoing interferometric observation to spatially resolve distant BCGs. We have 44 hours with NOEMA, and so more will come. And also I also presented you some projects concerning the galaxy supermassive black hole environment evolution, overmassive black holes in radio Loud AGN, and the fact that SMGs are excellent traces of distant protoclusters. In the future, in the next future, there will be strong synergy and multi-wavelength between Euclid, LST, and SKA. Euclid, in particular, we launched in July, and thousands of clusters and distant protoclusters are expected around radio Loud BCGs in the next decade. So a revolution in this field is expected, while we have only a few confirmed distant clusters today. So we can attack problems like radio mode AGN feedback and the formation of the first clusters in a systematic way. And I leave you. I leave it here, and I'm happy to answer the question.
Questions for the speaker?
Were you able to trace the nuclear activity in your sample? Were you able to trace the nuclear activity in your sample and link these properties with those of the environment?
Yeah, nuclear. You mean by radio or
radio, X-ray, optical?
No, in fact, no. In fact, that's. We weren't able to do both. I show you that, for example, for this radio Loud AGN sample, we were able to trace the growth region. To have an insight of the growth region. So we estimate the ratio, this emission, and so on. But we weren't able to probe the cluster environment. So it's very ambitious project. Yeah, that's why I think the multi-wavelength service in the future will help that we can tell if the source is in a cluster, what are the properties and so on. But yeah, to have both now, I think it's very challenging. Yeah. But yeah, we can discuss if you have some ideas for observation.
So Luca, can you say something about this PPM method to identify the cluster and proto-cluster? How does it work? So what do you need?
Okay, so yeah, so first I need I need the first photometric catalog, and that's why in fact we have to wait for new catalogs in the Poisson survey. So now they are building up catalogs in different surveys, and also I need positional prior. So. And also where it's key. So in these studies I use the radio galaxies, but in the study that I show you I use SMG. So a physical prior that is for which we have motivation that we are looking for over dense regions. It can be also used as for example post analysis. So if we have catalog or distant protoclusters, we can apply this method to see if we can detect independently the overdensity.
And there on the right, why you have these three strides at three different ratios?
Yeah, that's a good point. In fact, yeah. So the idea is that in fact if we are looking for a structure around given I mean, over density around given galaxy or position in the sky, we can also hope to detect a structure behind. So in fact, this method, I thought it a lot of time. It can be used as also a strategy to detect systematically length clusters. So, for example, or proto-cluster. For example, in this case, if we have a group or a rich cluster here, Redshift 1, but we also have a structure Redshift 2. So yeah, it could be used to detect systematically length proto-cluster. Yeah, that could be a possible application. Yeah, if you have some idea, we can discuss. Yeah.
Yes, right.
I have a curiosity. So if you go to the following plot, the one where there is a doubting.
Yes.
The object. So there is also a well-structured things that precious.
Yeah, of course. That's why I said that the yeah, I mean, of course, these are structure, yeah, over density, but that's why I say that we need a prior. Let's say we need a physically motivated prior. In this case, we have a position of the SMGs and the spectroscopic redshift. So if we have an overdensity in photo C at that given position and redshift, I mean, the measure of redshift is 0, so the chance that is chance alignment is small. While if we have a structure at high redshift, yeah, we can be real, but yeah, it relies on the quality of photo Cs, can be catastrophic and so on. But yeah, of course, it can be. I mean, as I said, it can be useful tool to find the unknowns. Yeah, so it can be real. Yeah.
Just to go on with this question, so what are the plans application to you? What are the priors that you plan to use?
Sorry.
What are the priors that you plan to use in the case of Euclid, just to apply this method to the Euclid data? So we have a photometric redshift catalog, of course, but
yeah,
the priors.
Euclid data alone, I think not before I thought about radio Loud. I mean, as I mentioned, radio sources from SAA. This could be a possibility, or also SMGs. I mean, there are new developments for RLAGN and NOEMA, so there is hope to have new SMGs detected in several surveys. So that could be another possibility. But yeah, the idea, I mean, the key idea that I have is to use in fact SKA, because there we will have thousands of radio Loud BCGs. Yeah. So if you look at the other cluster, 90% of them host radio galaxy. So yeah, and that's why at high redshift there is hope to that we discover many of these.
I have a very basic question. Is there a common definition of what a proto-cluster is?
Well, yeah, of course, no. I mean, I would say that there are let's say two definitions. One is a theoretical one that I mean, you fix Elon Musk and you say that it is the structure, every structure that is non-realized that will evolve in a realized structure by redshift 0 with a given mass above a given threshold, can be 10 to 14 solar masses.
So the requirement is 10 to the 14 at a large redshift?
No, I mean the structure at high redshift that will evolve by redshift 0 in a structure that is virialized and has a mass of above 10 to 14.
So you have to measure the mass at high redshift.
Yeah, exactly. The point is that you cannot measure the mass because it's not virialized. So it's and that's why you have confusion and so on. So the I mean the photometric redshifts. I mean there is a dilution of photometric redshift, so you are never sure of what the mass is. You have proxies. So the operative definition is to estimate over density. So that's what people say, and then they speculate that we evolve in a cluster.
You mean over density as a number of galaxies?
Yeah, a number of galaxies. Yeah.
So what's the number?
Well, I mean, it depends. I mean, depends on the depth of the survey. I mean, I can tell you that this structure that was spectroscopically confirmed by the et al. It's a 2.5 as a mass of a few 10 to 13 based on velocity dispersion, but there's just less than 10 sources detected in the beam. So it's it's really short noise regime. Yeah, that's the critical point. But maybe in the future with LST Euclid that it will be very different. As with GWST, we saw that there is hope to have I mean, there is hope to have to open new field. Yeah.
And Viviana, the last question.
When in BCGs, when you derive H2 mass from your observation.
Sorry, H2.
Yes, H2 mass from your observation. Do you use a specific excessive conversion factor, the Milky Way one?
Yeah, that's another good point. Yeah, I mean, I usually use the Milky Way one to have a homogeneous measurement, but yeah, of course, for star forming sources, we know that the alpha zero approaches the value of unity, so actually I test that. So other these possibilities and that. So for example, for kids, we have metallicity measurements, and we were able to see to estimate the alpha zero based on metallicity. I mean, there is a huge scatter as usual, so 2 or 3 it's unknown, but it's a limitation of the field. But yeah, I tend to prefer to use the alpha zero Milky Way to a homogeneous. But I want to say that, for example, for the excitation, it's the ratio, so this is less impact. So in some cases we can.
Okay.
Bypass the limitation.
Okay, I think that's it. Thanks again.